properties of ROC. Okay, so let's say we have a signal xt. Suppose you consider any point in the S-plane. Let's say this is the point. When can we say that the Laplace transform exists at this point? What is the condition? Laplace transform of xt is the Fourier transform of what? Fourier transform of xt into e to the power minus sigma t. Okay. And if you consider a point here, what is sigma? Sigma is what? S
Real
is sigma plus j omega. So S is this point. So what is the condition for existence of Laplace transform at this point? When you multiply, this is the condition, integral minus infinity to infinity e to the power minus sigma t, where sigma is this. This must be absolutely integrable. Is it? This is the condition for existence of Laplace transform. Now, can we say that if, suppose this converges for this value, can we say that if it converges, if the Laplace transform exists at this point, if you consider any point along this vertical line, the Laplace transform exists? Is it true?
Yes, sir.
Because if you consider any point along this line, its real part is sigma. Let's say sigma naught in this case. It is the same real part. So that is the first property of Laplace transform. So the ROC of Laplace transform. The shape of the ROC. The shape is always vertical strips. Like it cannot, we cannot have an ROC like something like this. It is not possible. It is not valid. It is if the Laplace transform, if one point is in the ROC, all the points along the line passing through vertical line passing through that point, that is also in the ROC. So the shape of the ROC is always some vertical strips. Okay. We cannot have an ROC like this or an ROC like this or something like that. It is not a valid ROC. The ROC is always something like this. It is not always greater than some point that we will discuss, but it is always, this shape is like this. If one point is in the ROC, all the points along the vertical line passing through that point is also in the ROC. Second property we have already discussed, that is if Xs is rational. If we can express it as a ratio of two polynomials in S, then roots of this numerator, those are called the zeros, and these are called the poles. Poles cannot be inside the ROC; they are always outside the ROC. But zeros may or may not be in the ROC. That is the second property. And the third property is that, okay, this is an interesting property. If we consider a finite duration signal, if xt is of finite duration, what is finite duration signal? What is finite duration? The signal is something like this. It is non-zero only in a finite interval. Some signal like this. And if the signal is of finite duration and if it is absolutely integrable, if it is finite, if a signal is absolute, by the way, if the signal is absolutely integrable, then which point is in the ROC? What does it mean? This is the S-plane sigma j omega. If you consider any point, let's say here real part is sigma naught. What is the condition for existence of Laplace transform at this point, or any point along this vertical line passing through that point? What is the condition? Is it this? Xt into e to the power minus sigma t dt, sigma naught t, that is finite? Is it that?
Yes, sir.
That is the condition for existence of Laplace transform at any point passing through this, any point along this line. Now, what does this mean? We are given a, we are given a signal that is absolutely integrable. What does it mean? Which point is in the ROC? Or which line is in the ROC?
The y-axis.
This line is in the ROC. We can say that if the signal is absolutely integrable, the imaginary axis, this is called the j omega axis, that is in the ROC. If a signal is absolutely integrable, the j omega axis is in the ROC. We have a signal xt that is finite duration. I am saying that finite duration means some arbitrary shape. You assume some arbitrary shape. It is from t1 to t2. It is non-zero. This is a signal xt. It is non-zero only in this interval t1 to t2, and it is zero outside this integral. That's why we call it a finite duration signal. Now, for a finite duration signal, it is given that the signal is absolutely integrable. That is, we can write that t1 to t2 mod xt dt, that is finite. It is given. That means if we consider the ROC, the S plane, this is sigma and j omega, this implies that the j omega axis is in the ROC. Is it? This implies that j omega axis is in the ROC. Now, if we consider any value here, let's say some value sigma naught greater than 0. Now, what is the condition for existence of Laplace transform here? Any point along this line? Is it this integral minus infinity to here we can write it as t1 to t2 because the signal xt is non-zero only in that interval, mod xt into e to the power minus sigma naught t dt. This is the condition. If this is finite, then we can say that Laplace transform exists here. Is it clear?
Yes, sir.
Okay. Now we are considering this case. If we consider sigma naught greater than 0, we have a signal xt. Let me take a different color. We are multiplying it with a decaying exponential, isn't it? We are multiplying with a decaying exponential, and the rate of decay that depends on the value of sigma naught. Anyway, it will be a decaying exponential. Okay. So if you look at this integral, mod of xt multiplied with a decaying exponential. Now what is the, and we know that the signal is non-zero only in this interval, t1 to t2. What is the maximum value of this exponential in this interval? Is it at this point? Because it is decaying exponential. Here t2 is greater than t1, so the maximum value is at here. Do you agree with that?
Yes, sir.
Okay. So what I am saying is, instead of multiplying with decaying exponential, I am multiplying with a constant value. That integral will be t1 to t2 mod xt e to the power minus sigma naught t1 dt. Instead of decaying exponential, I am multiplying with a constant signal. And we know that this exponential, these values always less than this. Now, can we say that this one is always less than this?
Yes, sir.
It is always less than this. What does it mean? So can we write this as this integral? I am writing it here. Integral t1 to t2 mod xt e to the power minus sigma naught t dt. That is the condition for existence of Laplace transform at this point. That is always less than this is a constant e to the power minus sigma naught t1 into integral t1 t2 mod xt dt. Is it that? What does it mean?
Yes, sir.
What about this? Is it finite?
Finite.
It is finite because it is given. The signal is of finite duration and it is absolutely integrable. Is it this? This is finite. What about this? Is it finite? Is it finite? Because T1 is finite, sigma naught is finite. If you consider any finite sigma naught and T1, this is always finite. T1 is always finite. Finite duration signal means it is some finite value T1 and T2. So this is finite, this is finite. What does it mean? Laplace transform at this point exists or what?
Exist.
So can we say that if we consider a finite duration signal and if it is absolutely integrable, if we consider any value, any sigma greater than 0, that is entire right half of that S plane, that is in the ROC. That is what we have proved here. If you take any value of sigma naught greater than 0, that is here in the right half of the S plane, it converges. Now what about this value? This value means you consider sigma naught here, that is sigma naught less than 0. Then what about the nature of this exponential? If sigma naught,
Growing.
it is a growing exponential. Okay, it will be a growing exponential. Now what is the maximum value of that growing exponential in this interval?
Value at T2.
It is the value at t2. So same using the same argument, we can say that this integral, if sigma naught is less than 0, then this is less than what? E to the power minus sigma naught t2 into integral t1 to t2 mod xt dt. Is it that? If sigma naught is less than 0, here only difference is that the maximum value of that exponential is now at t2. Earlier it was a decaying exponential, maximum value was here. So this argument, this we can write like this. What does it mean? Is it finite? We already know that this is finite because the signal is absolutely integrable. And what about this?
Finite.
It is finite. So what we have proved is if the signal is absolutely integrable, then the ROC is the entire S-plane. Is it? Everywhere in that S-plane that Laplace transform converges. It is in the ROC. That integral converges. Okay, so that is the first property. If the signal is a finite duration signal, for a finite duration signal, if it is absolutely integrable, then the ROC is the entire S-plane. That is the property. Take any finite duration signal. If it is an absolutely integrable signal, then it is entire S-plane. ROC is the entire S-plane. There is no other, we cannot have any other shape for the ROC. It is the entire S-plane. And remember, it is not necessary that this is finite, always finite. If it is not an absolutely integrable signal, then the Laplace transform does not exist anywhere in the S-plane. If it exists at one point, then it is the entire S-plane is in the ROC. That is what we have proved. Okay. Now let us consider a right-sided signal. right-sided signal means xt is something like this. Let's say I'm denoting it by t1. Right-sided signal means xt is equal to 0 for t less than t1. It is 0 up to here, then it is non-zero. And it is going up to infinity, because otherwise it will be a finite duration signal. That case we have already discussed. If it is not a finite duration signal, if it goes up to infinity, but it is 0 up to this point, then it is called a right-sided signal. Now, the property of ROC is that if we know that this converges at some point sigma naught, that means if we know that for a right-sided signal, the Laplace transform exists at this point. That means along any point along this line. That means we are given the information that integral minus infinity to infinity xt mod xt into e to the power minus sigma naught t dt, this is finite. Okay. If you are given the information that at this point it converges, this point is in the ROC. Now, if we consider any point sigma greater than sigma naught towards the right of this, what is the condition for existence of Laplace transform? At some point sigma, is it integral? Okay, another thing is that here we since it is a right-sided signal, the lower limit is t1. Okay, because it is signal is 0 up to here. So can we say that the condition for existence of Laplace transform at some point here towards the right of this point sigma naught, is it t1 into up to infinity mod xt e to the power minus sigma t dt? Is it that? Take any point sigma somewhere here. I am taking it sigma. Only condition is that I am assuming that sigma is greater than sigma naught. So it is somewhere anywhere here towards right of this. So if this condition is satisfied, then we can say that the Laplace transform exists. And we are given the information that it converges at this point. This point is in the ROC. This point in the ROC means all the points along this line are in the ROC. Now, can we write this in terms of sigma naught? Integral t1 to infinity mod xt e to the power minus sigma naught t into e to the power minus sigma naught t dt. Is it? I'm writing sigma
Yes,
t as like this. Because why I'm writing like this? Because we already know that this is finite. Okay, now we are writing it in terms of that. Now tell me, what is the nature of this? Is it a growing exponential or decaying exponential? We are assuming that the point is towards the right of sigma naught. So it is a
Decaying.
decaying exponential. That means you are multiplying this with a decaying exponential. Okay, and integration starts at t1. So what is the maximum value of this one? Is it at this point? Because it is always a decaying exponential. Maximum value is here. Is it? So can we write that this integral is always less than or equal to e to the power minus sigma naught into t1 into integral t1 to infinity mod xt e to the power minus sigma naught t dt? Can we write like this?
Yes, sir.
Using the same argument, whatever we have used earlier. This one. What does it mean? We know that this is finite. Sorry, where this is finite because this point in the ROC. So this integral is finite. What about this? Is it finite? T1 is finite,
sir.
sigma is finite, sigma naught is finite. It is finite. So what we can say, if it is a right-sided signal, if one point is in the ROC, we can say that everything towards the right of that is in the ROC. Is it? That is what we have proved here. If one point is in the ROC, all the points along that of a vertical line passing through that point is in the ROC. And if you consider any point towards the right of that line, it is always in the ROC. Is it? So can we say that the ROC is a ROC of a right-sided signal is also some right-sided ROC?
Yes, sir.
It is always right-sided. It cannot go up to infinity here because then it will be a two-sided signal. We have already proved that it is only for a two-sided signal, it is the entire ROC. So the ROC is the entire S-plane. So for a right-sided signal, the ROC is always right-sided. This will be the shape of the ROC. Now, what about a left-sided signal? Left-sided signal means it is 0 after xt is 0 after t naught, some time instant t naught. And the proof I am leaving it as an exercise. If it is a this is called a left-sided signal. It is non-zero up to some point, and after that it is 0. That is called a left-sided signal. For a left-sided signal, using the same arguments, you can prove that if one point is in the ROC, then everything towards the left of that is in the ROC. ROC is also left-sided. It is easy to remember. Right-sided signal, ROC is also right-sided. Left-sided signal, ROC is also left-sided. Okay? Is it clear? And we have already seen the example also, like e to the power minus AT ut. What is the ROC? It is real part of S greater than minus A. It is a right-sided ROC. And a left-sided signal, it is a left-sided ROC. So we have discussed the ROC of the shape of the ROC for three different types of signals. One is a finite duration signal. Okay. One is a finite duration signal. What is the ROC of finite duration signal?
S-plane.
It is the entire S-plane. Okay. Entire S-plane, the complete S-plane. And remember, finite duration signal doesn't mean that the Laplace transform always exists. The signal must be absolutely integrable. Okay. Then only it is the entire S-plane. And right-sided signal, ROC is what? ROC is also right-sided. So we can say that ROC of a right-sided signal is something like this. The ROC shape of the ROC is like it is real part of S greater than some, let's say I am writing it as sigma r. Some point sigma r. Okay. So it is then it is called a right-sided ROC. It is always right-sided. For a right-sided signal, it is, remember, it is not guaranteed that the Laplace transform always exists. If it exists at one point, then it exists at all the points towards the right of that. So the ROC is always right-sided. I can give you an example of a signal. This is also given in Oppenheim. If you consider a signal e to the power t square ut, you can verify that this doesn't have a Laplace transform representation. Okay. So it is not necessary that all the right-sided signals have Laplace transform, but if it exists, then the ROC is always a right-sided ROC. And for a left-sided signal, the ROC is always left-sided. It is the shape of the ROC is something like this, real part of S less than some sigma L. Okay. That is left-sided ROC. Now, What about a two-sided signal? Two-sided signal? Two-sided means it is infinite duration signal. Is it? Two-sided means infinite
Yes, sir.
duration signal. Because if it is not infinite duration, it will fall in one of these categories. One of these, either right-sided, left-sided, or finite duration. Infinite duration here means duration is infinite. Can we write it as a, let's say this is a signal. Can we write it as a signal, right-sided signal plus a left-sided signal? Can we write it as a sum of a right-sided signal and a left-sided signal? For example,
Yes.
if I split it like this, consider this as the left-sided signal and this as the right-sided signal. So this is a sum of a right-sided signal and a sum of and a left-sided signal. Is it?
Yes, sir.
So what is the shape of the ROC of this right-sided signal? It is like this. And this is towards left of some point sigma L. So the ROC of the sum of these two means sum of, it is the intersection of these two. Is it?
Yes, sir.
So the shape is always a vertical strip. And another thing, is it always the intersection? Sometimes the intersection is a null set, isn't it? When is that?
When sigma L is less than sigma R.
When sigma L is less than sigma R, then the Laplace transform does not exist. But if sigma L is greater than sigma R, this is sigma R and sigma L. Intersection will be something like this. It is a vertical strip. Okay. So we have discussed about 4 different types of signals. One is a finite duration signal. ROC is the entire S-plane. Right-sided signal ROC is right-sided. Left-sided signal ROC is left-sided. And for a finite duration signal, if the Laplace transform exists, then it is always a vertical strip. So these are the 4 possible shapes of ROCs. Take any signal, xt, if the Laplace transform exists, then the shape of the ROC will be one of these 4. Okay? Is it clear?
Yes, sir.
Yes, sir.
Okay. For a right-sided signal, I have said that it is towards right of some point like this. It is ROC is also right-sided. So what is this point XR? Sigma R. If you are given X of S, generally it is difficult to find this point. Where is this? But there is some point here. But if XS is rational, there is an important property. That means XS, if X of S, if we can write it as a ratio of 2 polynomials, then there is an important property. And one property we have already discussed, like zeros cannot be in the ROC and poles cannot be in the, poles cannot be in the ROC and zero may or may not be in the ROC. Okay. And if X of S is rational, there is an important property. That property says that the ROC is bounded by poles. Is bounded by poles or extends to infinity. Okay. ROC is always bounded by poles. If X of S is rational, ROC is bounded by poles, or if there is no pole, it extends up to infinity. Okay. Now we can you can see this e to the power minus at ut. What is the Laplace transform 1 upon s plus a? Okay. What type of signal is this?
Right side.
It is a right-sided signal. So ROC is also right-sided. So this property says that the ROC is always bounded by poles. So which is this point? What is the pole here? There is a pole
Minus
at minus A. So the ROC is real part of S greater than minus A because it is a right-sided signal. It is bounded by poles. Now suppose there are multiple poles. If you take some example like if x of s is 1 upon s plus 2 into s plus 1, there are two poles. Then can you tell me what is the shape of the ROC? If it is a right-sided signal, xt is a right-sided signal, ROC should be right-sided. Okay?
Yes, sir.
And poles cannot be in the ROC, and the ROC is bounded by poles. Then where is the ROC? What is the shape of the ROC? Can we say that in that
Most pole.
case it is to the right of the rightmost pole?
Yes, sir.
It is to the right of the rightmost pole because the pole cannot be in the ROC. ROC should be right-sided and it is bounded by poles. So the shape of the ROC is like this, to the right of the rightmost pole. And same for the left-sided signal. If it is a left-sided signal, then ROC is always what? Towards the left of the which pole?
Leftmost.
To the left of the leftmost pole.
So is it necessary that zeros and poles are always real?
No, it
Can't
is
they
not.
rely
It
on
is not necessary because S is a complex variable. It is not. I have just mentioned these points because if there is a pole here, draw a vertical line through that. This one is the ROC if ROC is right-sided.
Right.
Suppose you are given this information. This is the Laplace transform of a signal. And you are not given the ROC. What is the pole zero plot? There are only how many poles? There are two poles, one at -1 and other one at -2. What are the possible ROCs here? First of all, can it be the Laplace transform of a finite duration signal? Is it possible? You are given that some signal xt, its Laplace transform is 1 upon s plus 1 into s plus 2. Can it be the Laplace transform of a finite duration signal?
So because it is like ROC is not entire S-plane.
ROC cannot be the entire S-plane because there are 2 points, 2 poles here. Poles cannot be inside the ROC. So the ROC is not, we cannot have the entire ROC S-plane as the ROC. So this cannot be the the Laplace transform of a finite duration signal. Can it be a right-sided signal? What are the possible ROCs? Can it be a right-sided signal?
Yes, sir.
It can be a right-sided signal. In that case, what is the ROC?
-1. Right of minus.
It is, this is one possibility. When it is xt is right-sided. And what are the other possibilities? Can it be the Laplace transform of a left-sided signal?
Yes, sir.
Then what is the ROC?
Left of -2.
Left of -2. I am writing like this. This is possibility 2, that is left-sided. Can it be of an infinite duration signal?
Yes, sir.
Which one is the ROC?
-2 to -1.
It is this one is the ROC. That is third possibility. Okay. This we can write as 1 upon s plus 1 minus 1 upon s plus 2. Now using the standard results, we can find the corresponding signal. Okay, we'll discuss this in tomorrow's class. Okay. Any question?
So,
Yes, sir.
so for proving left-sided and right-sided,
Mm-hmm.
you use the fact that we are multiplying it with constant thing,
Mm-hmm.
but we can directly say now that if sigma is greater than sigma naught, then it will rapidly. So if for sigma naught it is finite, then for sigma also it will be.
If it is, yeah,
Directly.
in that case you can, but when you say that mathematically, this is the way to prove that. Intuitively, you can say that if it is, okay, you're right. If you multiply with some sigma naught, okay, any sigma naught, if it converges, if you consider any sigma greater than sigma naught, it is decaying rapidly. I mean, that decays faster than this, isn't it? Rate of decay is more, is it?
Yes,
So
sir.
it is always converging. If this is multiplication with this is converging, then it is always, this is always converging. You're right.